Hi, today I will demonstrate an example from AISpace using the tool for belief and decision networks. So AISpace has this amazing set of tools which can be used for learning and exploring concepts in artificial intelligence. It is developed at UBC under the direction of David Poole and Alan Meckworth. And this is the tool which we'll be using today to show variable elimination. So let's consider a scenario. We have a guy called Bill who's very particular about his morning newspaper. And of late he has been observing that the newspaper delivery has been kind of sporadic. So he says that the delivery of a newspaper is dependent on whether it has been successfully printed the previous night or not. And he comes up with two explanations for a paper not being printed. One is the usual malfunction at the printing press. The second one is kind of interesting, the end of civilization. If it's the end of civilization, then the paper will not be printed for sure. And then he assigns prior probabilities, and we do it as a belief network. So let's have a look. So this is the belief network that he comes up with. Okay, apparently it is maximized. Okay. Okay, so this is our belief network. Paper being delivered is dependent on whether the paper has been printed or not. The paper being printed is dependent on whether the printing press is fine or end of civilization as we know it. So the prior probabilities, okay, let's have a look at the prior probabilities. The prior probabilities for the printing press malfunctioning is sort of low. It's a 0.05 probability. The end of civilization is relatively high, which is like 0.001. And the function for paper printed is, so if the printing is malfunctioned is true, end of civilization is true, then the paper will not be printed for sure. All odds against us. And if the end of civilization is true, but the printing of malfunction is false, we still get no paper. However, if the printing malfunction is true and end of civilization is false, we still have a non-zero probability of paper being printed, and that is to account for cases when the printing press has been corrected in time for the paper, for the next day's paper. And if the printer has malfunctioned and it's the end of civilization, if the printer has not malfunctioned and if it's the end of civilization, then the delivery is almost certain. The non-zero probability for paper not being delivered is to account for cases like when the paper boy is not able to deliver or something like that. Okay. So let's consider the scenario where we observe that the paper has not been delivered. So paper delivered variable has been observed to be false, and we want to query what is the probability that it's the end of civilization. We go to verbose mode, and this is what we get. So this is the variable that we need to query, and this is our observed variable. So the initial factors we have is for printing malfunction. These are basically the prior probabilities for printing malfunction. Similarly for end of civilization, these are the prior probabilities. The F2 factor is the probabilities that we defined for the function paper printed, and it is dependent on printing malfunction and end of civilization. So that's why these three variables. And our F3 is dependent on paper delivered and paper printed. And so F3 is basically the conditional probability of paper delivered given paper printed, and our F2 factor is the probability of paper printed given printing malfunction and end of civilization. And these two are just the prior probabilities. So we will project observations on paper delivered. So notice that we had an F3 here, and right. So so paper delivered. So basically, paper delivered occurs only in F3, and when we project the observation, this has been eliminated, and we get only F4. Let's start summing out now. So we'll sum out printing malfunction first. And so printing malfunction is in factors F0 and F2. So F0 will be eliminated, and F2 will have only end of civilization in paper printed after it gets summed out. So it will form a new factor called F5 or something. So F5 is end of civilization in paper printed. Now we will sum out paper printed. So this is present in F4 and F5. F4 will be eliminated completely, and F5 would just be left with end of civilization since we're summing out paper printed. So that, and then we just multiply final factors, we normalize it, and we get a probability of 0.006. So observe that the prior probability for paper for end of civilization being true was 0.001. So after we observe that the paper has not been delivered today, it increases to a probability of 0.006. So that is one scenario. Let's look at some other case now. So what happens if we observe that it's the end of civilization, and so what happens to my paper delivered, right? So what do we expect? We expect that it's the end of civilization and the paper should not be delivered for certain. So we expect a probability of paper delivered true as 0, right? So let's look at what the applet does for us. So this is what we observe, and this is the variable that I'm trying to query. I do the usual project observations. I sum out printing malfunction first, I sum out paper printed next, and then I finally multiply the factors, normalize the factor, and I get what's expected, right? So the paper delivered to be true is 0. If it's the end of civilization, there would be no paper, obviously. Also observe that the maximum encountered factor size is 8. So what this means is that the maximum size of my factors, the number of variables which are present in my largest factor was 3, which led to 8 possibilities. So that gives me a maximum factor size of 8. Right, so we can do some interesting stuff. For instance, let's not observe anything here. Observation, none. Let's say the paper being printed is true, and I want to find out what is the probability of my paper being delivered. So I query that. So we can prune irrelevant variables here, since my subnetwork that I need to consider is only this, because these are basically not, they don't need to be considered. So I prune my network, and this is the only network that I need to consider. I project observations, and I get the result. So paper delivered is true with a probability of 0.9 if I observe that the paper printed is true, right? So let's see if this probability changes if I observe another variable. So I make observation to end of civilization, and I say that this is true, right? So let's query paper delivered. Verbose. Okay, we prune irrelevant variables, and we project. So observe that since my this variable was observed, even though I did observe these variable, even though I observed this variable, it was still not considered, because this is, so basically when I observe this, my network is independent of these two variables. So I just pruned that, and I still get the same subnetwork as in the previous case. So I should get the same probabilities. And so basically, if my paper printed is true, then no matter what happens to what I do to these variables, I still get the same probabilities for my paper being delivered. Close. So yeah, we can find out different conditional probabilities, and we can observe variables and do all sort of fun stuff.